Good evening.
Hi there.
Yeah, good evening, sir. I'm going to give a small welcome. So, good evening to everyone gathered here today, distinguished professors, respected educators, dear students, and honored guests joining us from around the world, and our chairperson, and also our managing director. And most importantly, Professor John Martinis, Nobel Laureate in Physics, Professor, on behalf of my school, Royal International School, on behalf of our academic community, and on behalf of a small island nation called Sri Lanka, it is my profound honor and deepest privilege to welcome you in this evening. Today is not merely a lecture, today is history, quiet, humble history being written. For our nation, for our school, and for me personally, this moment will remain unforgettable. I stand here as a student, yet today I carry a gratitude far greater than my age, my title, and my academic standing. This entire journey began not in a laboratory, nor in a grand hall, but in a simple classroom, professor. With a conversation with the teacher, from that moment a thought was born, and that thought slowly transformed into courage. So I began reading, I began learning, I ventured deep into the strange and beautiful world of quantum physics, into tunneling, coherence, and delicate boundaries where realities itself seemed to hesitate. Your work, Professor, was not merely something I studied, it became something that moved me. Your groundbreaking contribution from redefining our understanding of quantum tunneling to shaping the future of quantum computation showed me something extraordinary. The human curiosity, when pursued with discipline and humility, can alter the course of science itself. I hope you can agree, Professor, in that too. So that realization gave me the confidence to do something many hesitate to do. So write an email. A simple email, an innocent email, I must say. And yet you replied, Professor, and I'm really grateful for that. Professor, that single act, your willingness to respond, to listen, to engage, speaks as powerful as any equation or discovery in the history. It tells young mind across the world that science is not distant and greatness is not unreachable. Standing here today, I am fully aware of my insignificance in terms of academic achievement before you in the Sri, across the professors joining in Sri Lanka, researchers and university scholars whose knowledge far surpasses mine. Compared to them, I am merely a student. I stand unafraid because while my knowledge may be limited, my execution was not. And I'm proud of that, not with arrogance but with gratitude, for ideas mean little without action, and today proves that courage can bridge even the greatest distance. Professor Martinez, your presence here today, live, generous, and engaged, elevates this gathering beyond an event our school has ever hosted, and perhaps any school in our nation has ever hosted. This is not just an academic milestone, it is a message to every young mind. They are to ask, they are to reach, and they are to begin. We are deeply grateful for the time you have taken, Professor, the efforts you have made, and the respect you have shown to this community. May your words today inspire not only understanding but confidence to believe that even from a small island, greater conversations can begin. Before I conclude, Professor, allow me for a one final invitation. So, not as host, but as a son of this island, one day when time allows, not today, not tomorrow, perhaps not even soon, we would be honored beyond measure to welcome you to Sri Lanka one day, an island small in size but rich in warmth, nature, and hospitality. Until then, may this evening serves as our greatest first welcome with deepest respect, heartfelt gratitude, and lasting admiration. Professor John Martinis, we welcome you. Thank you.
Yes, thank you very much for your kind invitation, and it's nice to speak to you today. Um, I guess I'm going to have a format today where I will just talk for a few minutes about the experiment where we did the Nobel Prize, maybe make a few comments for students, and then we'll open up the question and answers. Is that okay?
Sure, sir.
Okay,
Yeah.
okay. So in terms of one more thing. I'm having some construction going on in my house, and the people doing the construction might cut off my internet, in which case, we'll just have to end, it'll be ended abruptly. So if that happens, it's okay. I unfortunately scheduled for construction for today. I think we're going to be okay, but just be aware of that. Okay.
Yeah.
I'm going to start with just sharing some, uh, a, I'm trying to, um, okay, I think I'm trying, yeah, let's see, I'm trying to get a share. Okay, great. I want to show some slides here. Okay. Can you see my first slide? Can I get some feedback here? Can you see my first slide?
Yes, sir. It's clearly visible.
Okay. I just want to say that this Nobel Prize was really motivated by the question, do macroscopic variables obey quantum mechanics? And we all know that quantum mechanics is the physics of atoms and molecules and fundamental particles and the like. But what we wanted to do was show that a macroscopic system like currents and voltages, variables, currents and voltages of an electronic device, could that see quantum mechanical behavior? And part of this was motivated by, say, the Schrödinger cat paradox, where you take an atomic system that decays in 50% chance in some time, and then if it decays, it kills a cat. And from the Schrödinger equation itself, you're then, before you open up the box, you're thinking, well, the cat could possibly be in a dead and alive state. This is kind of a strange idea. And the idea here was to see if it's really possible to have macroscopic variables obey quantum mechanics. And in doing this, we are looking at a small chip, which you see on the lower left on the side at the very bottom. There's a chip a size 1 millimeter by 1 millimeter that has a Josephson junction. And that Josephson junction is then connected up to room temperature electronics. And then you measure what happens to the Josephson junction switching from the superconducting state to the normal state and looking for macroscopic quantum effects coming from that. And, I'll say that when we did the experiment, we were able to show that although at high temperatures, it thermally escapes from the 0 voltage state to the voltage state. At low temperature, the escape rate levels off in a way that's quite consistent with what you expect from the tunneling phenomenon. And also what we did was put on microwaves, which enhances the escape rate from the 0 voltage state to the voltage state. And these enhancement of the escape rates has a resonant behavior of when the driving microwave frequency is equal to an energy level transition. And this is purely a quantum effect, seeing these discrete energy levels, and kind of presents a very clear qualitative demonstration that the system is obeying quantum mechanics. And of course, this is very interesting because once you see energy levels, you can then, over the 40 years since this experiment, look at, make qubits out of these and do more sophisticated experiment. So the way I like to think about this is, although we have quantum mechanics that we can see in the natural world, and this is exhibited in a periodic table, how the electrons form the shells and the states around the nuclei, and you can build quantum systems out of atoms. What we have here is a new system where out of capacitors, inductors, transmission lines, Josephson junctions, we can build these new artificial atoms and quantum devices that one can do quantum physics with. So you've kind of expanded the periodic table over which you can do physics experiments. And over the years, the people have looked at also mechanical systems, connected it to photonics, optical photons, nanomagnets. So there's a lot of very interesting experiments that have been done over the years to take advantage of the fact that quantum mechanics is much more general than the behavior of atoms and molecules. It really is a generic behavior of physical systems where if you get it into the right conditions, you can see the quantum mechanical behaviors. So over the years, we've been working on this. And in my career, what was very exciting after many decades of work, we've been able to build quantum computers. And at Google, I was really fortunate to be involved in the quantum supremacy experiment, where we're thinking about this macroscopic test in a new way to test whether macroscopic quantum computation does actually work and like as we expect from theory. And here with 53 qubits, you have a total computation space or Hilbert space of about 10 to 16. So this really shows you can do a powerful quantum computer. And now many groups around the world are working how to put this together and make a useful quantum computer and to expand the ideas and expand the ideas of computation. So at this point, let me stop my sharing, and I can ask any questions about my talk or in general about science. And I think that would be a nice way to continue with the discussion.
Ah,
Great.
so Professor Martinez, thank you to hear the description of the architecture of this quantum tunneling and the uh, quantum physics behind this quantum computing concept. So as a high school students, I am really impressed by how far this quantum world has taken our imagination to. So with me, I have Amaya, one of my school colleague. So she will be joining with me for a small Q&A too. So from my side, I do have a small question, Professor. So, Professor, what was like as high school students, we are engaged in different activities, and also as students, as university students, we are engaged in different activities. So, what was the fuel that spirited your way into the quantum realm, the quantum world? What was the first spark that you got that, like, I have to go into this and I have to work, and there's something behind, like, there's something calling that I have to find what's that call and what's behind that call, and like there's something to discover. So what was it, Professor?
Sure. Uh, of course, physics, there's a lot of different subjects you have to learn, but probably the most interesting subject you learn is quantum physics. And nowadays, they have nice books that you can read to kind of understand that at a rudimentary level, a simple level. But in order to understand it, very deeply, it takes some math, for example, linear algebra and differential equations and things like that, that, it's kind of a little bit beyond what you do. Although I think you can learn a lot about quantum mechanics without that. So what happens is in the university, typically the quantum mechanics course is at the beginning of your third year out of a 4-year degree. And I can just say that when you get into a formal course and really trying to learn this very deeply, it's kind of one of the most interesting courses you take as an undergraduate. And also you take this in graduate school too. It's a very deep subject. So it does take some math, but it's really interesting once you get into it. And partly it's because the laws are very strange about it. You have to learn about wave functions, and then you do operations on the wave functions to measure probabilities that you would do in an experiment. And you have to kind of learn how this happens. So all I can say is it's really interesting to learn about it. You have to get comfortable with a lot of mathematics to understand it. And you take it as an undergraduate, and then you go into graduate school and you take a more sophisticated course of quantum mechanics. Okay, and you go even deeper into it, which again is a fascinating course. It's the best course as a graduate student. And what happened with me is, of course, with this quantum mechanics being very interesting, um, I was kind of, interested to do some research into quantum mechanics as for my PhD research. And what was very interesting is I had a course from John Clark, which is the co-Nobel Prize winner this year. And he was beginning to do measurements, seeing quantum mechanical effects in electronic devices. In the beginning, they were looking at quantum noise effects. And then with my experiment that, was awarded the Nobel Prize for, we also saw tunneling and energy level quantization, the full quantum effects of this. And what I would say is partly I was interested because when you take quantum physics, you're very interested in studying it professionally, doing experiments, because then you're going to learn much more deeply the physics. And I would say because of my thesis experiment and because of working on superconducting qubits, I have a much deeper understanding, I would say almost an intuitive understanding like right now, similar to what I see with mechanics or electromagnetic theory, which is something you take even at high school a little bit. And certainly as a freshman, you take that. So I get a much deeper appreciation. The other reason I like this is because my hobby was electronics in high school. And I built a lot of circuits. I remember looking at a book that told you how to design circuits, which was great because for the first time in my life, I could use all the mathematics that I learned to actually build something and get it to work. And that was a really big event for me as a high school student. So I really enjoyed that I could continue learning about quantum mechanics, both in my thesis and during my years trying to build a quantum computer. And one of the nice things about quantum computers is it's like a single qubit and a few qubit systems. This can be described mathematically a little bit more simply than for like the hydrogen atom. And you can get much more intuition about how the system works. And you can connect it to some classical concepts to kind of understand how it works better. So yeah, it's basically been an opportunity for me to learn more and more about this fascinating subject for my whole career.
I see, Professor, what led you here. So that's very interesting, like uh, how how like as a high school student, you got that opportunity to do do the research, and that interested you, and also after coming to the PhD level, that's super amazing. And as a high school student, we always dream of it, to do some research that we all uh, as inspired about. So one more, like, the catch up question. So I think many of students, like university students in here, and also high school students, and also maybe other young scientific community here, want to hear, like, from your experience, Professor. So what advice could you offer these um, to this community present here, trying to identify what they truly love? So as you mentioned, like how this quantum mechanics and the max part, and also the research like uh, drive you forward. So so, so how will the high school students and university students should recognize what truly they love, and so they can go beyond what the classical understanding is, to find something like this. Well,
Sure. So let me answer the question in a different way. If you want to do something like this and do research, what do you have to do to be able to do, world-class research, okay, or do research? And the thing that I like to tell even undergraduates, and this is high school too, is that to do research requires you to know a lot of physics, and it requires you to learn skills way beyond the classes you have taken. So you've been in school for a long time, you're in high school, you're going to go to university. Some of you, I hope many of you, it's a great experience. You're going to learn physics. If it, and even with a university degree, it's hard to know enough to do independent research. So you go to grad school, you take one or two more years of class, and then you start training yourself to do research. And I'm saying it's usually 4, 5, maybe 6 years as a graduate student that teaches you how to do research. And then you can start doing it independently. And then, of course, you go off into whatever job you're going to do, and you continue to learn to do research. And I'm kind of retirement age almost, and I'm still learning how to do research better and learning how to work in it. So it's a lifetime occupation, which of course makes it really fun. Now, what I would say is, you want to, if you can get into research, it's good to do that as early as possible. However, it's hard because you don't know very much. It's hard to imagine after many years, even in the university, you don't know very much. However, like at UC Santa Barbara, it's very possible to do research project for your senior thesis. And that's really, really nice to do. And sometimes it's pretty straightforward research, but it gets you started to do that. In terms of high school, it's very hard to have the opportunity to do research, but I do want to say there's something you can do, okay? And I'm going to talk first for an experimentalist like myself, and that is to learn how to build things. Because if you know how to build things, then when you go to research, you're always building something new. You'll know how to build it faster and better. Also, if someone wants to hire you, a professor wants to hire you, if you know how to build things as an experimentalist, you will, they'll want to hire you because they know you can be productive right away. So in high school, I did a lot of electronics hobbying. I was always building little projects in my garage. These days, you have access to computers, and learning how to program, or I would say robotics is a very good field because they have relatively inexpensive kits, and you learn how to do programming and you learn hardware, like electronics, the same thing. You can build actual hardware. I'm sure there's many other things you can do that would be your interest. And I would say in high school, you're in the astronomy club, okay? So, if you can help build hardware or fix the telescope or, various things like this, or even learn how the telescope works in great detail, learn how to program it properly. That's really, really valuable. And I'm going to say in high school, the first few years as an undergraduate, you really focus on your classes and try to do well. It's very almost theoretical. But in high school, you really have a chance to learn how to build things. And that's pretty close to doing experiments. Okay. And I would say that's really giving you a good background to see if you like it and to build up your skills and make you more hireable when the time comes. Now that's for experimentalists. I think for theorists, it's a little bit harder to do that. Certainly you can study papers and the like, but I would say everyone these days needs to know how to program a computer. And if you're theoretically oriented, then there's a lot of computer theory you might be able to do and learn how to write programs and get good at that. Because I would say modern theory requires a lot of knowledge of how to be able to use a computer. And you should learn how to use it well in high school, obviously. That's going to help you for your entire career. Does
Yeah.
that help you?
Yes, Professor. It reminds me of the projects we have done in our schools, and also the lectures. Some of the lectures I have attended with the professors that said about the research, like they corresponds to the betterment of the scientific journey we have. So it's very
Right.
interesting to know how as high school students we can engage in experiments, and unknowingly we have done many experiments in our high school, like
Yeah.
knowing the telescope and all. Yeah, it's very interesting. So at this point
There,
I'm
there was
delighted.
there
Yeah.
was one more thing that I'm going to advise high school and undergraduate students to do. Okay. And this has to do with being, if you want to be a physicist, what's really great about being a physicist is you're always solving kind of new problems. Okay, so you take something, some phenomenon, and then you have to think about it and apply mathematics and solve for the equations and maybe do some testing and the like. But let's just say when you start, there's basically no formulas, right? You just have to understand things. This is very different, I think, than engineering, where you're generally taught certain solution methods for doing it. Now, if you want to be a physicist, which is really fun, it's because you're always solving new problems. You can be very creative. It means you have to train yourself to solve problems. And you should start in high school and as an undergraduate and graduate student, learn that. And then when you do as a researcher, you have to really solve problems from scratch. Now, in my day, that was pretty straightforward to do. Okay. But students these days are at a big disadvantage here. Okay. And your disadvantage is if you have a physics problem, you can look it up on the internet and get the solution. And my understanding is like most any problem out there, you can get at least a close enough that'll tell you how to solve it. And you're shaking your head. Thank you. Okay, now I want to tell you this is really bad for your physics career in the sense that you need 6, 8 years of practice of how he's solving problems just by yourself. Um, uh, uh, that. So the question here is, should you be using internet solutions to solve your homework problems. And I'm recommending, insisting that you don't use it. Do not use it, because then you are not training yourself to solve problems. This is why you do physics. I mean, maybe for engineering and other fields, it's fine. But for physics, you're always trying to discover and understand something new. So you have to try to figure out the problems on yourself. And that's how you learn physics very deeply. It's the way we do it, solving problems. Now, sometimes you can't solve a problem, and I understand. And what we did in graduate student school is we had study groups. We got together with one or two or three or four other people and worked on the problem together. And that's actually good, because when you do real physics, it's usually in a group. So that's fine. But you really have to, if you have, you want to do that. And I'm going to say, if, at the very end, if you can't get it, it's probably better to look it up to understand the solution than not to turn in your homework, okay? Because then you'll learn something. But you learn so much less by doing it. It should just be a small fraction of your problems if you can do that.
Yeah,
Does that make sense?
yeah.
Am I clear on that?
Yes, Professor. It's very clear. Yeah. Like the problem, like the problem you address right now, and the insistence that you gave, like about using AI and also Google and also this internet on using homework. Obviously, frankly, I should admit that I'm using too the internet for some questions when like when the deadline is near, or like when I doesn't have time. Or, I think so that's
Yeah.
the biggest disadvantage, like as high school students, like we have. So we have everything near us, so we can just with a click away we can just find out what is wrong and what is correct. So obviously that's a disadvantage, and also affects our creativity of the brain, and also the deepness that we can go through. So with that, I think Amaya, you may have some questions to Professor Martinis too, and I guess one of my classmates may join with me. So uh, with her joining until she asks her question, uh, my another question is, Professor. So, uh, how does this? You talked about the collaboration with other students, and also how it affects the learning capability of students. So, as also you work with the other Nobel laureates who got the physics prize for 2025, as John Clark, and also Professor John Clark, and also Professor Michel Devoret, if I'm correct with the pronunciation. And so like working with them and also working in Google, how like the collaboration, how did it affect this journey on making this discovery? And was it positive, was it negative, or how was it?
Oh, so working with other people is definitely a positive. And I'm going to say, when I'm in graduate school, you usually start off on an experiment by yourself, which is a good thing because you have to learn how to build and do the experiment. But when we started work with Michel Devoret, and of course, you always have an advisor, so John Clark was there. But when I started working with Michel Devoret, it was very clear from the absolute beginning that working with really good people and uh, doing this is such a great benefit. And part of the reason is, if you have some ideas, you have to share it with someone else. You have to communicate it. And what happens with physics, and this is why you want to work with groups, is that when you have to share your ideas, you have to explain it well, which is a skill you have to learn how to do. But also the other people kind of give you feedback, whether it makes sense or whether they understand it. And it helps clarify your ideas very well. The other thing I found working with Michelle is he thinks differently than I do. He learned physics in France, which is very different than learning physics in the United States. And because of that, he would have a certain way of thinking about it, and I would have another way to think about it. And we talked together, and then the combination of the two was much more powerful uh, than uh, than the possibility there. So this is a very good thing. Different people have different ideas, and just learning how to explain something often clarifies your own ideas and makes it more clear.
And yes, sir. So collaboration is really positive. I myself engage when there's a lot of people to work with. Like they have different ideas actually that drive our focus in different angles and makes even a single project all rounding perfectly smooth project. Like they know something that I don't know, and I know something that they don't know. Like
Yeah.
likewise that's how it works. As
But yeah, the important thing though is if they know something you don't know, you need to learn from them
yeah.
to enhance your knowledge and skill set and the like. So that's what's great about collaboration. It's very natural to teach each other.
Yes. And also, so moving on to a question in the Q&A, our managing director has asked, Professor, what excites you most about the future of quantum technology?
Yes, so um, I I helped start this field of quantum technologies 40 years ago, although it was only until, let's say, the 1990s that it really started to get interesting with theoretical work saying that you could build a quantum computer, at least for me. So I've been working on this a long time, and the field is continuing to grow. And there's more and more efforts around the world to build this. Now, for me, the big issue is building a quantum computer, and to build, a very complicated supercomputer. Quantum supercomputer is a really complicated project involving theorists, computer scientists, engineers, physicists, and I find it really fascinating to work with this large group of people in order to figure out how to build this. My particular skill is kind of understanding the system engineering and figuring out how everything gets put together, kind of understand all the physics and engineering. Uh, and I find that very enjoyable and fun. For young people, you can get into quantum computing. Generally, there are some technicians you need to hire. Okay, that would maybe be a 2-year degree after high school. Also, technicians after a 4-year degree. They are master students we hire who have a little bit more skills. And then if you really want to be involved in the research and inventing the new things, then that's generally having a PhD. So there's lots of different opportunities. There's industrial labs, like I worked at Google. There's IBM and startups like our startup or Rigetti and Superduck Qubits, many other startups. So there's lots of opportunities. I don't know if there's anything in Sri Lanka. I know there is some efforts in India, but certainly in China, United States, Europe, there's lots of opportunities there.
Yes, thank you, Professor. So one small question from me, like as international students, like from an island like Sri Lanka, what opportunities lies in these universities? Like high school students, I have heard of summer programs too. Like what opportunities like we have to interact with high-level professors like you all, if there's any chance, and also to learn from you all, like this very lecture we are having. Are there any opportunities that we are not aware that you are aware, sir?
So I didn't quite understand the question. I'm sorry.
So, Professor, like there are opportunities like around the world to interact with high-level professors like you all in the
Yeah, yeah,
scientific
okay.
community. So, are there any opportunities that we are not aware as international students? In like there are maybe opportunities in America, like summer programs that they are holding. So, are there any
Yeah,
opportunities that we are not aware?
yeah, I'm sorry, I don't know about the summer programs in the United States. I know that they have various programs in the United States at the universities, and there are some research opportunities. But generally, I know those are for U.S. students. But I think some of them would look at international students. I don't know how to find them, but there are programs, and you should definitely, think about doing that if that interests you. I'm going to say, though, as a high school student or as an undergraduate, if you're interested in this subject, you don't have to do a quantum computing internship. Just doing a regular internship, you get used to maybe doing lab research in some other field that will teach you how to do, let's say, experiments or do calculations or do computer simulations. And then if you go to like a graduate school, then with that experience, you're more likely to get in graduate school and you're more likely to get hired by a quantum group. So don't feel that you have to have quantum experience as an undergraduate high school student. If you can, that's great. But just any experience building things, doing research, I just recommend people always consider that because it takes a while to learn that skill.
Yeah. Yes, Professor. I understand that. So we have a lot of Q&A coming, and I hope Amaya could ask one of those. Like they are really brilliant questions, very deep ones. So Amaya, are you here?
Yes. Well, thank you, Sulochana, for handing over. So, firstly, a very good evening to you, sir, Professor John. So, as we have some time restrictions, I'll quickly move on to the questions that have been directed in the Q&A. And Professor Martinez, the first question is, does the observer effect have anything to do with the consciousness? And there has been a follow-up question for that, which is that which interpretation of wave function collapse do you believe in?
Okay. Um, so for the first question, um, when I think about the brain, of course, there's quantum effects in the chemistry of the brain, but it's so hard to build a quantum computer. It's hard to imagine this messy organic system in your brain has some macroscopic quantum effects or like people have suggested that, and which is a nice theory. But as an experimentalist who see how hard it is to build a quantum computer, it would have to be very simple, like sensory things that's helping you with consciousness, maybe not the essential feature. So the second question again was,
So it was about which interpretation of wave function collapse
oh
do you
yeah,
believe in?
okay. Um, yes, so let me just say that the experiment I did in my thesis had to do with the wave function collapse. And the idea by Professor Leggett, who proposed it, was that macroscopic variables just don't obey quantum mechanics, and that's where the collapse was. Well, we showed that that idea was wrong, but it was still an interesting experiment. My interpretation of the collapse is something that a few physicists believe, a lot don't, but I think it explains it. There's a very nice textbook by Serge Haroche and Ramon. Haroche won the Nobel Prize, called Exploring the Quantum, where he it's a graduate text, so it's hard, but he kind of shows that when you um, when you do a measurement of a system, you couple a microscopic system to a macroscopic system, let's say like a needle, okay? And when you have something like a needle that's very macroscopic, he calls it a pointer state. Uh, then what happens is you lose coherence of that macroscopic variable extremely quickly, so that that's what collapses that pointer state either to one state or the other, because of the sensitivity of these macroscopic measurement states to noise and just various imperfections to the environment, and that explains it. So for me, it comes out of a very natural explanation of how the Schrödinger equation works and how quantum mechanics works. Is that okay?
Yes, Professor, I think that answered the question that was asked.
Oh,
Well,
by the
so
way, I wanna say, for me personally, when I think about my quantum system, I don't necessarily think of all that complexity. I break quantum mechanics up into the two components, that of the wave function and it changing in time according to the Schrödinger equation, and then the measurement, where you collapse the state by doing a measurement. And that's the standard interpretation, where you have kind of quantum mechanics as two parts, and you can just calculate and understand experiments that way. And then I know that the measurement part probably is connected to the Schrödinger equation in some way. But again, this is still debated by people, and that's good. I mean, I think we need a better understanding of this.
absolutely, Professor. So moving on to the third question tonight, it goes as this is by a student who's involved in a postgraduate research in optimization and optimal control for robotic manipulation, and it's math intensive, and they do consider about the fundamental physics leading to all the algorithms, cost functions, and so on, yet they are more focused in an applied sense. And the question is, Professor, whether you think it's possible to direct this research towards the physics aspect of it, or whether the gap between engineering research and physics research is too high.
Um, so I'm very interested if someone has a physics background doing robotics, because I was at a conference, actually it was in Davos World Economic Forum last week, and I was talking to someone I used to work with who is now in the robotics. She's a physicist, quantum physicist, and now doing robotics. And she was telling me that her special knowledge of physics is really, really good for robotics. Okay, and that they need more physicists in robotics. This is in Google, by the way. So this is a really serious effort that they're doing. And the problem is most of the people in robotics are just software engineers, and they just think about software. And then you have a few engineers who do the build the hardware. But someone integrating the software to the hardware and kind of understanding maybe how to think about the system is something that, again, you're asking and answering fundamental questions, is something physicists do really well. So this is the nice thing about physics, is there's a lot of different occupations you can go into because you know how to solve problems in an unusual way. And robotics, it sounds like that's something that if you're a physicist would be a really interesting field to go into. And obviously that's a huge field, practical field of the future. It's very important. It's probably pretty well paid too. Okay, so this is something I would recommend physicists to think about.
So thank you for that insight that you provided. Professor, and this question is that so basically when it comes to Sri Lanka in advanced levels, particle physics is taught only in advanced level courses, but how can we teach these quantum mechanics and these theories for primary students so that they can learn it from an early stage, receiving a competitive advantage and having a better shot at understanding it better?
Yeah, that's something that I wish could be taught better. When you take regular quantum mechanics, it's taught from, let's say, understanding how the hydrogen atom works and things like that, which is really important because that's what quantum mechanics is very good for. However, I think you could teach it from the points of qubits for two-level states and maybe two-level states and harmonic oscillators, okay, which is taught in the basic courses. And I think if you were to teach it that way, you could get the concepts, and then you could use quantum computers as a student. You have very access to like single qubit quantum computers. And I have a feeling that that might be a little bit more intuitive and easier to understand the basic concepts of quantum mechanics. And then, of course, you have to know how the hydrogen atom works and understand that. So I'm hoping eventually that's how quantum mechanics will be taught. And it could be taught, the mathematics is not so complicated. So I'm hoping that that's how it could be taught in an initial class. I don't know if there are books out there. I don't know if people have taught it that way, and I know other people have talked about it. But that's something I think would be really helpful, because the mathematics and the concepts are not so complicated. For example, when you just talk about a two-level system, you can talk about the state of the system in terms of a vector on a sphere, which is much easier to understand because it's so visual. So, and I use that kind of thinking all the time. So, yeah, that would be helpful.
Thank you, Professor. And this is the fourth question for tonight, which is that Professor Martinis, your career has been a masterclass in turning impossible theories into tangible reality. And it is truly inspiring to have a builder of your caliber with us today. And so I'm truly honored to be doing this Q&A session with you today too. So for a long time, quantum effects were thought to belong only to tiny particles. When you first saw clear quantum tunneling in an electrical circuit, something you could actually build and hold, what was your reaction? Did it feel exciting, unsettling, or just deeply satisfying?
So what was great about my thesis experiment is that we approached it in the sense that we didn't know whether we'd see quantum mechanics or not. And we treated it as a very fundamental question. And then we treated it that we wanted to give a very definitive answer, where we could put error bars and say it was or wasn't a phenomenon. And as such, we thought about alternative theories, such as what would be the classical behavior, or what would be if there was quantum noise instead of regular quantum mechanics talking about describing it. So I would say that was the best part, is we treated it as a very fundamental experiment. And then we thought very carefully about the physics and how to measure things very carefully, and then to numerically compare our results to the theoretical prediction. So it was a very pure experiment that you don't, and with lots of unknown concepts and engineering ideas behind it. And that was the real joy in figuring out. Now, what happened is we initially did the experiment at high temperature, took some data. It made no sense at all from our understanding of the theory. And then we had to understand noise filtering and electrical engineering. And then we, just really thought carefully about what was the physics, which is microwave engineering in the end. And then once we did that and redesigned the experiment, everything worked. And it was just, one experiment after the other that was working, because we had understood what was going on. So the whole concept of like understanding the physics and then seeing it displayed in the experiment you're doing is really quite a wonderful thing, because then you can understand what's going on.
Dear Professor, before we move on to the rest of the questions, I can see that our Q&A box and our chat has been spammed. So, Professor, before we move on, could I please know how many more questions that you would be willing to answer so that we'd be able to pick from them?
Yeah, we can go on for a little bit more. These questions are very nice. Thank you. So
Thank
let's go beyond the hour.
We should
okay.
appreciate.
Thank you so much for your kindness. I think all of us would take the maximum out of this because it's, of course, an once in a lifetime opportunity. So, thank you, Professor. Then, Professor John, moving on to the questions in the Q&A box again. Uh, this is by a student who's interested in exploring post-quantum cryptography for his final year research. And as he's new to the specific field, he was wondering if you could suggest a beginner-friendly area with PQC, perhaps regarding implementation that would be suitable for a student project.
Yeah, that's a really good question. And that this is very much a mathematical question, post-quantum cryptography, and it would be accessible. Now, that's a theory project that I don't know about. Of course, if you want to look in post-quantum cryptography, you should look at the NIST website in the United States. It's a group that's looking at post-quantum cryptography and kind of researching into that and verifying whether the algorithms are good or not. So, you know, I don't, probably someone has looked at that, but that's the database. But I don't know if there are simple explanations or not. That's not in my field, and I'm not doing it. But I know it's very important. Now, one of the things they don't know, the student may not know, is people have been implementing post-quantum cryptography, you know, in various platforms. I think Google does it. IBM has hardware to do this and the like. So this is getting deployed, not widely, but it is available. But you know, it's important that people continue to think about it. And I would say once you get to, you know, a graduate's level research, it's important that people investigate this to make sure that it's really a secure protocol. But at the beginning, I'm sorry, I don't have a good answer there.
Well, Professor, this question has been directed where in large-scale superconducting quantum processors, how do you see the trade-off between surface code error correction and overhead and hardware-level sense suppression evolving? And do you believe that there's a fundamental noise floor that will ultimately limit fault-tolerant scalability?
Thank you. That's a great question. I like the surface code because it's relatively straightforward to understand, and you have, you know, one qubit connected to the nearest neighbor, so it's something we can build. But more importantly, surface code has been around for a long time, so people have done lots and lots of analysis on it. And we know that it works well. Of course, we have to test it and the like. People are trying, the only problem with the surface code is that you have to use a lot of qubits in order to have the low error rate of the logical qubit that you're doing. So, you know, maybe a typical number is about 1,000, okay. Now, people are trying to do codes that are more efficient numerical-wise than that, and those are coming out. The problem is they haven't done a full analysis of that. So for example, if you have a new kind of code, can you build a classical computer that's fast enough that can actually look at the errors and decode what the errors are? You have to think about what happens if one of your qubits is dead. It's bad. Is the whole code, you know, then blown up? Okay. Whereas the surface code can tolerate, I think, 1 or 2% errors, dropout errors, and still work properly. So there's a lot of research into this, but there are many what I call system parameters, many things you have to get right to get it to work. not just, the number of physical qubits per logical qubit. So it's an active area of research right now. Now, what we're doing is we're doing our designs around the surface code because he thinks it's very practical. And then if someone comes up with a better code or a better variant, then we will use that. But what I found in my career is once we understood the surface code, then kind of I knew what we had to build. And I think that's still the case.
Thank you, Professor. For the sixth question, this is something I think which is very practical for all of us, and I think we've always been there. So sometimes solving a hard problem relies on looking at the problem from a different angle. Sometimes, no matter how much we try, how hard we try, we can't reach a solution. And the question is how we can build the intuition on looking at a problem from different angles.
Yeah, you obviously have to do that. And, I don't have any advice on how to do that. That's just something that once you solve many, many problems, you understand how to look at it different angles. And, then you're more likely to come up with a new idea. Again, working with other people is very important. So, yeah, that's a that's a really it's kind of an intuitive thing that you learn how to do, and yeah, so I can't give a specific algorithm for that.
No, Professor, I think it's fine. I think it's
Yeah, that's a
one of
good
those
question,
things.
though.
Yeah,
Good
I mean,
question.
it comes with practice by your own self. But thank you so much, Professor. And Professor, while I was watching your lecture too, I was wondering about this too, and I saw this question popped up in the Q&A box, which is, what do you expect the discovery of quantum tunneling could lead to in the future?
So quantum tunneling, of course, is used to explain how radioactive alpha decay works. You also use electron tunneling in modern electronic devices. So it's it's used all the time. In terms of quantum computing, it's not used too often. This question's kind of hard to answer. Usually you look at some kind of energy level transitions to think about how the quantum computer works.
Okay, Professor. Professor Martinis, this question is directed by a student from Sri Lanka with the ambition to become a professor and work in NASA-related research in the United States. And as an international student from a developing country, what academic pathway would you recommend in terms of degrees, a research focus, and institutions? And what qualifications or experiences does NASA typically value for someone aiming to contribute at a professional research level?
So the thing about quantum computing is you need to have a wide skill set to do that. I mean, for superconducting quantum computing, you need to know quantum mechanics and qubit physics, but you also need to know about electronics. You need to know about electromagnetic theory and microwave theory. Something about waveform control, signal processing helps. If you're into more the laser physics, you then have to know a lot about optics and lasers. So, it turns out, the a typical undergraduate physics program touches on all those subjects, and you really need to learn a lot of subjects to understand this well. And of course, computer programming and, some computer science background and understanding is very useful.
Professor, for one last question, we will be directing for tonight. So as you know, in your Nobel Prize lecture, you spoke about how progress in physics often comes not from sudden breakthroughs, but from years of careful refinement, failure, and iteration. And at a point like quantum physics, the journey behind is far more greater than what the destination could lead. So, looking back on your own journey, a professor, was there a moment where persistency mattered more than brilliance? A time when contentment felt uncertain yet proved essential. So, this could technically be used as a form of motivation for the young kids out there who should aim for the stars to do whatever they want in the field of quantum physics.
My inspiration really came just as a student, enjoying math and science. I was very fortunate to go to a special kind of science camp every week for a couple hours that helped me do that. I would say I was really motivated because of my father always was doing projects, building things in the garage, and I was helping him and learning that. And I kind of have an intuitive feeling for mechanics and physics from that. And then when I took, high school physics, it's like, well, I kind of knew the concepts. I just had to learn how to put the math to it. So kind of being able to understand how things work intuitively very much helped me. So yeah, I would just say as a student, young student, I was just noticing. Okay, the other thing I need to note is one of the things my parents told me all the time was to ask questions. Okay, and in fact, when we sat around the dinner table, and instead of them saying, what did you do today, they always asked me, did you ask any questions today? And that's kind of unusual, but as a scientist, that's what you do all the time. You're always asking questions about everything you're doing. And, you go to a conference and you want to ask questions to really understand, what people are presenting. So I would say, to encourage that habit within yourself, that it's good, it's okay to ask questions is good. I think I have time for like one more question.
Now, Amaya, I think so. Professor, to end with this question, I think of connecting AI to quantum. So, Professor Martinez, in quantum physics, we accept uncertainty as a fundamental. So while in artificial intelligence, we often try to eliminate uncertainty through optimization and prediction, if I'm correct. Do you think, Professor, there is a future we are embracing quantum uncertainty rather than correcting for it could fundamentally change how we design intelligent systems?
Yeah, clearly, what's interesting, AI and large language models embrace probabilities, and they fit whatever they are to the model they already have, and they give you probabilities for, let's say, what the next word would be in some discussion. So yeah, I think people are embracing uncertainty more now with AI because it's kind of how the models work properly.
Yeah, thank you, Professor. So
Okay.
yeah, thank you very much, Professor. Like it's connecting AI to quantum is like one of my dreams too, what I aspire of uh, making someday and becoming someday. So Professor, before we conclude this, before I give my closing address, is there any specific thought that came to your mind of like not to miss this or any remarks and a final thing you would like to give to this young scientific minds in here? I think we from high school level to graduate level to we came across the postgraduate level too, and also some PhD levels in here. So we have covered a whole lot of angle here from starting from high school. That's great. That was very interesting. Like I never thought it would go to such a level, starting from there. So over to you, Professor.
Yeah, I'll just conclude here to say that it's really kind of amazing that I can be a student for my whole life, learning things, discovering things, and get paid for it and have a, a nice life out of this. There's no guarantee because it's hard to be a scientist. It's very competitive, but it's a very worthwhile thing to do, and it's great. I always considered studying physics that I might go into more engineering fields and that I would learn a lot of physics and can do that too. And that could have been a career path for me if things had turned out a little bit differently, and I would have been very happy with that. I think being a scientist and being a physicist is best match for me, but it's really amazing to, be able to, study and learn and invent things for your whole career. It's just a wonderful occupation.
Professor, before the closing remark is delivered by Sulochana, I'd like to say when you answered the final question about how curiosity was something that was really important in your family, I think the audience today delivered it really well with all the wonderful questions they asked. So, Professor, thank you so much for answering. I'd say this has been an awesome opportunity that I would look back on every single day. I'm truly honored to have having had this conversation with you. Professor, once again, thank you so much. And now I'd like to hand over this for Sulochana to deliver the closing remarks.
Okay.
So, Professor, formally to conclude, Amaya, thank you for your help throughout. I really appreciate that. And Professor Martinis, on behalf of our school, our students, our teachers, our parents, and every curious mind that joined us tonight, thank you. So today was not just a lecture or a session or a discussion. It was a moment where science felt human, where curiosity felt possible, and where distance disappeared. And also from my point of view, like I was traveling, walking, living in a walking distance to my school. I was walking to my school, and I thought of crossing the road by myself or using the subway. Then I thought, today I'm going for something amazing today, so I should not take even a 1% of a risk while attending to this. So with my that motivation, I took the subway for myself and got here. That was my motivation. So you reminded us that great discoveries do not begin in laboratory alone, but in questions, discipline, and also some patience, as you described. And that lessons will stay with us far beyond tonight. And for many of us here, this was once in a lifetime opportunity. And I deeply appreciate that. And for some, it may be the beginning of a lifetime journey in science. We are deeply grateful for your time, your generosity, and your willingness to engage with us, not as an audience, but as thinkers. Thank you for trusting us with your insights, Professor. Thank you for inspiring Sri Lanka tonight. And thank you for reminding us what is possible when curiosity meets purpose. We wish you continued success, good health, and many more discoveries ahead. This conversation will live with us for a very long time. Thank you, Professor Martinez. Yeah.
Thank you very much. It was my pleasure to talk to you today. Okay.
Hi, Professor. Have a nice day.
Okay.
Good day.
Bye-bye. Thank you. Good day.
So with that, we have come to our conclusion of today's session. Hope you have learned something more and taken something into your life, and hoping to start research on science field. And cheers for many more to come. Thank you very much.